12:45 during our class time. And again, same as before, submission is due until 1 p.m., meaning you have extra 15 minutes to scan and upload. So that's the time. And make sure you submit before 1 p.m. because late submission is not accepted. All right, so make sure you do that. It's better to submit something that's not perfect than not submitting at all. Right? Okay, and the coverage, lecture 7.3 to 10.7. That's the coverage, 7.3 to 10.7. And how to access the exam is still exactly the same on Canvas. Okay, let me see if I can show you. Maybe I can join from a different computer of mine and show you the Canvas page. Start. All right, okay, I'm gonna share a new screen with you. Screen number 2. Okay, so now you go to Canvas and our class is 304, section number 1. Change to student view. All right, so this is what everybody should be able to see. And then same as before, you go to assignments, right? Go to assignments and scroll to the bottom of the page and you should be able to see midterm 2, November 9th. Click on it and you will see it's locked until November the 9th at 11:30 a.m. Okay, that's it. Then when the time comes, you'll be able to see the PDF file. Same as our midterm 1. Exactly the same. All right. Quit this meeting. Okay. Come back here. Okay, can you guys still hear me?
Yeah,
we can hear.
Okay. All right. Share screen again. All right. Okay. And then we're gonna do a quick review. Right. First topic, control volume. That's chapter 5, control volume. Okay. What is the opposite of the control volume? Does anyone remember? We have two kinds of system where we have two kinds, right? Control volume versus anyone?
Open system.
Closed system.
Closed, very good, right? Closed. So under chapter 5, we learned, okay, what if we have a control volume? The diagram on top of the screen is a pipe. It's a pipe where you have inlet. The mass flow rate coming in is m dot I. And on the right, you have m dot E, which is the mass flow rate leaving. And A is the cross-sectional area. How do you calculate cross-sectional area if you have a circular pipe? What is the cross-sectional area of a circular pipe? Anyone?
Pi r squared?
Yeah, pi r squared. Or if you prefer to use diameter, it should be what? Pi d squared over 4. Okay, it's up to you. All right, so under control volumes, we learned two equations. The first one is conservation of mass equation. Sigma m dot I minus sigma m dot E equal to dmCV over dt, right? mCV stands for mass of the control volume. And m dot I is the mass flow rate at the inlet. M dot E is the mass flow rate at the exit. Why do each of them have a sigma sign? What does the sigma sign tell you? What
So it's
do
the
they mean?
sum of all masses going in and out of the control volume?
Yeah, you may have more than one inlet and more than one outlet. If that's the case, you just sigma up all the inlets and then sigma up all the outlets. Okay, that's why the sigma sign is there. Okay, what if we have steady state? What's going to happen to this equation?
The energy will equal 0.
Which part?
The kinetic and the potential.
No, yeah, we're talking about conservation of mass equation.
Oh.
Steady state.
All the properties go to 0.
Therefore, yes, the right-hand side goes to 0. Right? If the steady state right-hand side goes to 0, and in short, it's going to become what? M dot I equal to M dot E. The mass flow rate coming in will be equal to the mass flow rate leaving. That's what you get out of the steady state. Right? If you have 10 kilograms coming in, then you will have 10 kilograms leave. Right? Steady state, conservation of mass equation. And the second one, equation we introduced under control volume was what? First law. All right, first law. Okay. First law. So now, if you have a control volume, the first law becomes longer, right? Q, we still know what it is. Q dot heat transfer rate. What about W dot CV? W dot CV is control volume work per unit time, right? The dot on top of it means divided by time. What is W dot CV? Where does it come from? Where does W dot CV come from? Two words. Anyone? What's the reason for M dot CV? So for example, if you have a pipe, just like the diagram at the center of the screen, do you have any W dot CV?
Isn't it moving parts?
Yes, very good. W dot CV comes from moving parts. If your system does not have any moving parts, then W dot CV will just be equal to 0, and that's it. If you have a pipe, inside a pipe, there's no moving parts. What is a moving part? Like piston moving up or down, the blades rotating inside a turbine, those are moving parts. However, if you do not have any of them, such as in a pipe, then this term W dot CV must be 0. Right? Remember that, it's going to make the calculation very quick. Okay, and those two terms we already know, right? Q dot heat transfer, W dot work, and then you plus what? The total energy brought in at the inlet. Total energy brought in at the inlet has three components. They are enthalpy, H, kinetic energy, 1 over 2 V squared, and potential, GZ. So that's the total energy brought in at the inlet. Therefore, it has a plus sign. And then the same thing happens at the exit. However, energy leaves at the exit. Therefore, you have a negative sign, subtraction. Subtract the total energy lost at the exit. And again, same three terms, enthalpy, kinetic, and potential. Right-hand side, dE over dt. Right, so that's our first law. If you have a control volume, steady state, what's going to happen?
D over dt becomes 0.
Yeah, right-hand side goes to 0 if it is steady state. And there's one more thing that will happen to this equation, dE, if it is steady state. M dot I will be
Same as m dot e.
yeah, same as m dot e. Very good. Don't forget that. Right? It's going to make the equation much, much easier if you have a steady state. Okay, so at this moment, there's one thing I want to remind you, very important. What is that? When you need to use first law to do analysis, now you have to think which one do you use, right? Before this chapter, the first law we learned was Q minus W equal to delta E, which is the short version of first law. And now you have option number 2. Option 1 versus option number 2. Which one do you use? You have to be very, very careful before you start doing the calculation. Otherwise, everything below that will be wrong. Okay? So what is the rule? When do you choose option 1? When do you choose option 2?
Option one, when there is a closed system, and for option two, when we have a control volume, like an
Very
inlet and
good.
outlet.
Yeah, very good. So before you apply first law, the first thing you have to identify what kind of system do you have. If you have a closed system, then you have to use option number 1, the short version of first law. If you are dealing with a control volume, however, where you have inlet and outlet, then you must use option number 2, the longer version of first law. If such choice is wrong, then everything below that will be wrong. Okay, and that's going to cost you a lot of points. So one thing I want everyone to keep in mind is, again, before choosing first law, you have to double check which one applies to this question. Is it option number 1 or option number 2? Take a few minutes to think before you start writing, so that everything below that will be correct. Okay, I don't want everyone to get a wrong start. All right, so that's very, very, very important. Choose the correct version of first law based on what kind of system you have. Okay, any questions so far? This is chapter 5. Under control volume, we learned two things: conservation of mass equation and first law. No? Okay, and then next one, mass flow rate. How do we calculate mass flow rate? M dot rho v A. What is rho?
1 over density? No, it's density.
Yeah, rho is density, right? But in this class, usually we don't deal with density. We deal with what?
Specific volume, which
Yeah,
is 1 over density.
Yeah, so we replace rho with 1 over nu. That's usually the case, right? What is V?
Velocity.
Velocity. Some of you may mixed up with what? Volume. That's not volume. Right? Rho VA, the V means velocity. Okay, and A is the cross-sectional area. So this is how you usually calculate mass flow rate. Rho VA. V is velocity. Okay. All right. Okay. A is geometry, so you can easily calculate. What about nu? Right, nu. Do you have a plan for nu? Nu is a, yeah, it's very good. A material property, right? If you want to look for property, you have to first identify the face. For example, if it is point F, you know you're going to look for nu F. If it is point G, you know you're going to look for nu G. If it is superheated, how do you look for the nu? Superheated.
Table A4.
Very good. Table A4. And when you use table A4, you have to have 2 inputs. Usually those 2 inputs are temperature and pressure. And then what if it is a mixture? How do you plan to look for nu?
Table 8, no.
If it is a mixture, how do you plan to
we
look
use
for nu?
what's called again purity.
Yes, it's not
Purity.
called purity, but called quality. Right?
Right.
Quality.
Quality.
If it is
So
a
one minus
mixture,
quality, you add.
yeah, very good. This is the equation. If it is a mixture, you have to come to this equation to look for the corresponding nu. X is called quality, not purity. Quality. Okay, quality. All right, so that's everything under chapter 5. Any questions? No. Okay, and then we move on to the next chapter, chapter 6. Right, chapter 6, Carnot cycle. Carnot cycle. Okay, and one thing before we start the 4 process, we need to remind you. Once you see the Carnot, the word Carnot, don't forget there is one hidden equation. What is that? Right here. If it is Carnot, based on the definition, we know every single step it is what? Reversible. If every single step is reversible, then your actual efficiency eta must be equal to what? The maximum efficiency you can ever reach. And what is maximum efficiency? 1 minus Tc over Th. So if you see the word Carnot, keep in mind you have this equation to use. Okay, Tc and Th, Tc is the cold temperature, Th is the high temperature. And then when you plug in the temperatures into this equation, what do you have to make sure? They're both in what kind of unit?
Kelvin.
Yes, Kelvin, right? It cannot be anything else. It cannot be Fahrenheit, cannot be Celsius. It has to be Kelvin for both of them. Otherwise, your solution will be wrong. Right? Okay, so after that, let's go over the 4 steps for our Carnot cycle. We have 4 steps. You can just think of the 4 strokes in an engine, right? So process 4-1, it's called isothermal expansion. What does isothermal mean?
Doesn't that mean that pressure is constant? No. Same temperature.
Isothermal. Iso means the same.
Same temperature, I think?
Yes, isothermal means same temperature, constant temperature. Okay. 1-2, adiabatic expansion. What does adiabatic mean?
No mass transfer.
No. Adiabatic.
No heat
Oh,
No.
shoot.
No,
No
what?
heat transfer. my
Yes,
bad.
no heat transfer. Adiabatic means no heat transfer. Q is equal to 0. Okay, and then 2-3, isothermal compression. If you take a look, 2-3 is the opposite of 4-1. 4-1 is isothermal expansion. Then 2-3, being the opposite, is isothermal compression. And same thing happens to 3-4. 3-4, adiabatic compression is actually the opposite of 1-2. 1-2 is adiabatic expansion, so 3-4 will be adiabatic compression. Okay, so that's the 4 steps. You can think of the 4 strokes in the engine, which we will talk more at the end of this class. Okay, and then let's go to Carnot cycle. Under Carnot cycle, we have 2 examples. The first one is the engines, where everything is considered as a closed system. The second example on the right-hand side is for a power plant. In a power plant, every single step out of the 4 is a control volume. So that's the difference between the two examples we did in class. On the left, for the engine, it's Carnot cycle, but it is applied to a closed system, such as the engines. On the right-hand side, it is also Carnot cycle, but this Carnot cycle is applied to power plants, where every single step is a control volume, not closed. Okay, so let's do the first one. All right, do the first one, engine first. Okay, so first of all, we sketched the P versus nu diagram. And we do not need the vapor dome anymore for this case. Does anyone remember why?
It's all superheated.
Yes, everything is superheated. So everything is to the right side of the vapor dome. If that's the case, we don't have to draw the vapor dome anymore. Okay, so we have two constant temperature lines, TH and a TC. The one hot is on top. So TH is on top. Okay, 4 to 1. Remember what is 4 to 1? Isothermal expansion. Isothermal means temperature is the same. So 4 to 1 must remain on the same temperature line, TH line. And then it is expansion process. So what's going to happen to my x coordinate? Nu.
It's gonna get bigger.
That's why 4 to 1 must move to the
Right.
right. Very good. Right. 4 to 1 stays on TH line and move to the right. Okay, that's 4 to 1. 1 to 2. Remember 1 to 2 is called adiabatic expansion. Adiabatic expansion. So expansion, what's going to happen to my y coordinate pressure? If the gas expands, the pressure will go down. So 1 to 2 must go down. Next, 1 to 2 is called adiabatic expansion. So nu, my x coordinate, will become bigger. That's why 1 to 2 not only has to go down, but also has to go to the right, because the volume becomes bigger. So 1 to 2 must go down and be curved to the right. Okay, 2 to 3. Let's remember what is the name of 2 to 3.
Isothermal compression.
Yes, very good. Isothermal compression. So isothermal, they have to.
Professor?
Yes.
Just a quick question. Why is it curved from 1 to 2 and 3 to 4 and not a straight line?
1 to 2 is curved because 1 to 2 is curved to the right because the x coordinate is nu, which is specific volume, which is volume over mass. During 1 to 2, 1 to 2 is called adiabatic expansion, meaning volume becomes bigger. Therefore, your nu will become bigger. If your x coordinate becomes bigger, you have to move to the right.
Okay, but why isn't it a straight line going from
why
1 to
this?
2?
So 1 to 2, 1 to 2, we usually sketch 1 to 2 as a curved line and curved to the right. This is 1 to 2. And your question is, how come 1 to 2 is not a straight line curved to the right? That's your question. Because PVN equal to constant. That's usually the case. It's called polytropic process, where the
Okay.
index n is not equal to 1. Right? So that's why it's a curve usually.
Got it. Thank you.
Okay, yeah, no problem. All right, very good question. Okay, and 2 to 3, let's go back to 2 to 3. Isothermal compression. Isothermal meaning the temperature doesn't change. Therefore, 2 to 3 has to remain on the TC line. And then isothermal compression. What happens to my nu if it is compression?
Goes to the left.
Smaller. That's why 2 to 3 has to go to the left along this TC line. Okay, and then 3 to 4? 3 to 4 is called adiabatic compression. Right, compression. What's going to happen to my pressure? If you compress it, yeah, pressure goes up. Therefore, 3 to 4 must go up. In addition to moving up, what's going to happen to my x coordinate?
It also moves to the left because it's compressing.
Yeah, 3 to 4 is adiabatic compression. So volume becomes smaller. 3 to 4, therefore, has to go to the left. Right, so 3 to 4 not only goes up, but also moves to the left.
Down.
Okay, so that's the diagram. Okay, and one thing I noticed in grading your homework is I noticed if you sketch this diagram, 1 to 2 and 3 to 4, they must be curved. They must be curved. What I noticed in your homework is, okay, 4 to 1 and 1 to 2, straight line. 2 to 3 and 3 to 4, straight line. This is not correct, right? 3 to 4, 1 to 2, they're not vertical lines. They must be curved. They must be curved. If you do not sketch them as curved, that means you do not understand they are compression and expansion processes. Okay, so make sure you draw exactly what you mean. Okay, all right, so that's the first case. Any questions? Any questions? No? Okay, so this is Carnot cycle applied to a closed system, which is also the case for your homework number 4, problem number 3, also a closed system. Okay, the second example was also Carnot cycle, but this Carnot cycle is applied to a power plant. What are the 4 components in the power plant? 4 to 1 is the boiler, where you gain heat. And after boiler, you have 1 to 2. What is 1 to 2?
Steam turbine.
Very good. 1 to 2 is the turbine in which the gas will, the steam will expand. Okay, 1 to 2. And then 2 to 3? What is 2 to
Condenser.
3? Yes, 2 to 3 is the condenser. That's where you lose the heat. Okay, last one, 3 to 4 is the
Pump.
pump. Okay, so that's the 4 components in the power plant. And if you take a look at each component, boiler, do you have an inlet and outlet? This is the boiler. You do have an inlet and outlet. Therefore, boiler is a control volume. And 1 to 2, steam turbine. Again, you have an inlet, outlet. It's a control volume. 2 to 3 is a condenser. You have hot water goes in, cold water comes out. Also, you have inlet and outlet, which is the control volume. Last one, pump. Same as before, you have inlet, outlet. So every single step in this example is a control volume as opposed to closed system. That's the difference between those 2 examples. Okay, so let's sketch 1 to 2. 4 to 1 first. 4 to 1 is the boiler. And number 4 is always at point F. So you just use point F is point 4. And then 4 to 1 is called isothermal expansion. Isothermal, what does that tell you? 4 to 1 has to remain on the
Constant
TH line.
temperature line.
Yeah, and then number 1, usually at this moment, we call it point G. Okay, so 4 to 1 is pretty straightforward. It doesn't change. Point 4 at this moment is F, and point 1 at this moment is point G. So you don't have to worry too much about it. Okay, and then 1 to 2. 1 to 2 is called what is it called? Adiabatic expansion. Adiabatic expansion. And how do we sketch 1 to 2 then? Still the same as before. Still the same as before. It must be curved to the right and going down. And number 2 ends up as, what is the face of number 2?
Mixture.
Mixture. Be very careful here. Okay. All right, 2 to 3, same as before. Isothermal. So 2 to 3 has to remain on this TC line, and which is a straight line. Pretty good. And then number 3 is also a mixture. 3 to 4 has to curve up and to the left again. Same reason. Adiabatic compression. Exactly the same reason. Okay. So if you take a look at the 2 diagrams, they all have the same shape. Right? Only difference is between 4 to 1 and a 2 to 3. Okay.
Professor, I have a question.
Okay.
So for a controlled volume or a power plant in the Carnot cycle,
Mm-hmm.
can we assume that the pressure and temperature are equal from 4 to 1? And
From 4 to 1, what is constant?
we know that temperature is constant, but from the looks of it here, pressure also looks constant.
Very good. That's true.
So can we
Just by
assume-
looking at, you don't have to assume anything. Just by reading this diagram, you notice 4 to 1 is a horizontal line, right? It's a horizontal line. If it is horizontal line, they must share the same y coordinate. And what is my y coordinate? Pressure. So it tells you what? P1 is equal to P4. That's correct. And then if you take a look at number 2 and number 3, you can reach the same conclusion. P2 is equal to P3, which is true. Yeah, what you noticed is not an assumption, but absolute truth. Very good, which we will talk even more later on. All right, 4 to 1 is the boiler. Inside a boiler, the pressure is always constant. 2 to 3 is the condenser, and inside the condenser, the pressure is always constant as well. Okay, very good question. What you noticed is the absolute truth, not an assumption at all. All right, very good. Okay, any other questions? But if you, like you just said, 4 to 1 is also on which line? TH line, meaning they have the same temperature. And 2 to 3, they're both on TC line, meaning they have the same temperature. So for 0.4 and 0.1, not only they have the same temperature, but also the same pressure. Isn't that interesting? Okay, any other questions? Right. Since we're here, I can ask you one more question if you want to take one step further. So by looking at this diagram, 4 to 1, we know they share the same temperature. They share the same pressure. But remember, what is 4 to 1? 4 to 1 is the boiler. That's where cold water goes in, hot water comes out. That's 4 to 1. But 4 to 1, they have the same pressure. They have the same temperature. Where's my heat? Right, from 4 to 1, you're adding heat to the water inside the boiler. As you add heat to the water, the temperature remains the same. The pressure remains the same. What is going on? Right. Usually when we add heat to something, the temperature or the pressure will go up. How come? From 4 to 1, that's the boiler, where you add heat. The temperature doesn't change. The pressure doesn't change. What is going on? Where is my heat used for? Right? Where's my heat? What has my heat been used for? The temperature and pressure are not going up. So what is the heat used for? Anyone? The heat is used for phase changing. What is the phase of number 4?
Point
Liquid.
F.
Yeah, point F, which is liquid. What is the phase of number 1? Point G. What do we call point G? Saturated vapor. So number 4 is liquid. Number 1 is vapor. So that's where the heat has been used for. The heat is used not to change temperature, not to change pressure, but used to change the phase from liquid to vapor. Okay. All right. It's a very good question. Anything else? Any other questions? No. Okay. And the one thing we realize is the area of the enclosure, right, as in the green shade. What does it mean? Area of the enclosure for each one of them, they have the same meaning, which is W cycle per unit mass. Okay, W cycle per unit mass. The area of the enclosure is W cycle per unit mass. What is W cycle? W cycle is just the net work output from your cycle. So for example, if you have a power plant, then this W cycle is just what? The amount of electricity you can produce. If you have an engine, if you have a car engine, then this W cycle is just the net amount of work produced by the engine which you use to drive the car. Okay, W cycle is the purpose of any cycle. W cycle is what you want to get. W cycle is what we pay for. We want it to be as big as possible. Okay, so if you see a different cycle with a bigger enclosure area, is that a good thing or bad thing? Anyone? If you see the by just looking at the enclosure area, the bigger it is, the better it is, right? Because the bigger the enclosure is, the bigger W cycle is, and W cycle is what we want. Okay. All right. Any questions at this moment? No. All right. Okay. And then what you need to do is what you need to be able to perform is to look for the Q, heat transfer, and work, W, for every single step. What is the heat transfer? What is the work of every single step out of the 4 steps? Okay. All right. So let's do a quick example. We'll use the power plant as the example. Okay. The control volume one. Process 4 to 1. What is the Q dot? What is the W dot CV for process 4 to 1? Do you have a plan? We use the power plant as one example. Now, going through process 4 to 1. What is the Q dot? What is the W dot CV for 4 to 1?
W dot CV would be 0 since it's the boiler, right?
Yes, because it's a boiler and there's no No.
No moving parts.
Yeah, very good. No moving parts. Therefore, this term is 0. Very good. It's quick, right? Very quick. Okay, after knowing W dot CV is equal to 0, what's your plan for Q dot?
Use the long version of the first law.
Very
Or sorry,
good.
yeah.
Very good. All right, Q and W, if you have any one of them and look for the next one, the other one, always use first law. Okay, so when you use first law, you now have two options. Be very careful. Which one do we choose? The long version, because it is a power plant. Everything is a control volume. Okay, if you use the engine as one example, you now have W, you look for Q. What equation do you use? Still first law. However, which one? Which version? The short one. The short one, just like in your homework for problem number 3. You dealt with an engine. So when you use first law to look for W or Q, you have to use the short version of first law. Okay, right, that's it. You should be able to do, so what you need to do is to go through every single step. What is the Q and a W for every single step? You should practice, all right? Okay, so that's what you need to do, looking for work and heat transfer of every single step. All right, any questions? No? All right, okay, next one, Clausius inequality. Okay, Clausius inequality. What is Clausius inequality? Clausius inequality is just the mathematical expression of second law. Right. If you design a system, not only you have to obey first law, which is conservation of energy, you also have to obey second law of thermodynamics. And what is second law of thermodynamics? We introduced 3 different expressions, and they're both pretty long, pretty abstract to understand. But in short, every process in this world has a direction, such as getting old. So that's second law. And we have a mathematical expression of second law, which is Clausius inequality. You can use this equation to calculate what? Sigma. Sigma will tell you if your design obeys second law or violates second law. All right, doesn't remember the rule? If sigma is equal to 0, what does that say about your system?
It's perfectly efficient, right?
Yes, and the word is reversible. If your
Reversible, yeah.
sigma is equal to 0, it's called reversible. Your design is reversible. If your sigma is greater than 0, what does that mean?
Impossible.
Not impossible?
It's just aging normally.
Yeah,
It's not
yeah.
reversible.
Oh. Yes, very good. You can just think of sigma as what? Your change of age. If your sigma is equal to 0, right, meaning your age doesn't change, you stay at the same age forever, that's the ideal case. That's called reversible. If your sigma is greater than 0, meaning, okay, you get older, which is what? Normal. Sigma greater than 0, meaning irreversible, which is everything in this world. And sigma less than 0, right? Your change of age is negative, meaning you become younger. Then this process must be what? Impossible. Okay. So if your sigma is equal to 0, meaning reversible. If your sigma is greater than 0, meaning irreversible, which is everything in this world. If your sigma is less than 0, right, becoming younger, it means impossible because your system violates second law of thermodynamics. So if you design a new engine and you check the sigma, if your sigma is greater than 0, then that means your design is correct. However, if your sigma is less than 0 for an engine you designed, what does that say? That means the design is wrong. The design won't work because it violates second law. Okay, so in Clausius inequality, calculating sigma is a mathematical expression of second law. Okay, just like first law, right? We have an equation for first law. This is the equation for second law. All right, so you should be able to calculate sigma, and from the solution of sigma, you will be able to tell if your design is feasible or not feasible. Okay, if your solution for sigma is negative, that means your design is wrong. It violates second law. It will never work. All right. Okay. Any questions so far regarding Clausius inequality? No? Okay. And then the next topic was TS diagram. What is S? What is S?
Entropy or
Yeah, it's very good. Entropy, specific entropy, very good, right? So the way we sketch the TS diagram is pretty much the same as T versus nu diagram. The only difference is you just have to change the x coordinate from nu to S. Everything else is the same. You have a vapor dome, you have constant pressure lines, P1 versus P2. Which one is higher, P1 or P2? P1 or P2? What's the rule? The higher this line is, the higher the pressure it represents. So in this case, P1 is higher. Okay. 4 to 1, let's use the power plant as an example. 4 to 1 is still the same. Number 4 is point F, number 1 is point G. But 1 to 2 has changed. 1 to 2 has changed. Right. Before, on the P versus nu diagram, top right corner of your screen, 1 to 2 is curved to the right, and 3 to 4 is curved to the left because the volume has changed. But if you have T versus S diagram, the x coordinate is no longer volume, but entropy. And for this case, both 1 to 2 and 3 to 4 will be vertical lines. And you can watch the videos to find out why on the T versus S diagram, 1 to 2 and 3 to 4 are both vertical lines. Okay, does anyone remember? What's the reason? One word. Isentropic.
Tropic.
Yeah, that's the word, right? So if you haven't watched that video, make sure you go over that video and it explains why on the T versus S diagram, 1 to 2 and 3 to 4 are both vertical lines. And this diagram is much, much better than the P versus nu diagram before. Why? Because we know the area of the enclosure means what? W cycle per unit mass. And if you move on to this diagram, T versus S diagram, it means the same thing. The area of the enclosure on this T versus S diagram means exactly the same thing, which is W cycle per unit mass. However, this diagram is much better. Why? Because the enclosure is a perfect what? Rectangle. And we can actually calculate the area of a rectangle. If you use the diagram P versus nu, okay, although we know the area of the enclosure tells us W cycle per unit mass, there's no way for us to calculate the numerical solution of the area because 1 to 2 and 3 to 4 are curved. So this is an irregular shape. That's why usually we prefer to have T versus S diagram, especially towards the end of the class. Okay, all right, so next, how do we calculate the area of this rectangle? 1, 2, 3, 4, enclosed by 1, 2, 3, 4. What is the height? The height must be TH minus TC. And what is the length of the rectangle? S1 minus S4. Okay. Okay. What's your plan for TH and TC? How do you plan to look for TH and TC?
Use the tables.
How?
You're gonna find TF and TG, or at the F and G point, and that's gonna be 4 and 1.
There's no TF or TG, but we call it, what is it? So usually P1 and P2 are given to you, right? So if you know P1, how do you find TH? Table?
A2,
A3?
A3,
A3, you start from the pressure and look for what in the table?
saturated temperature.
Yeah, the corresponding saturated temperature. And that is your TH. All right, that's it. What about T code? What's your plan? Use table A3 and pressure P2. Look for the corresponding saturation temperature. And this corresponding saturation temperature will be your TC. Okay, that's it. That's how you look for TH and a TC. And make sure they are, when you do the calculation, they're both in what? SI unit, which is Kelvin. Okay, S1 and S4, what's your plan? Do you have a plan for S1 and S4? By looking at this diagram, S1 is equal to, what's the phase of number 1?
Saturated vapor.
Yeah, very good. Right. What about number 4? S4 is equal to, what's the face of number 4?
Saturated liquid.
Yes. Right. So S1 is just equal to S1G and S4 is equal to S4F. And if you're dealing with point F or point G, you can easily find them from the tables. Okay. All right. That's it. Okay. S1G. Then you just go to table A3. And what do we know about number 1? P1. That's it. Okay. What about number 4? What do we know about number 4? Do we know the temperature or pressure on number 4? P4 is given to you. Why? P4 is equal to?
F the
What is the
F
pressure of
point,
number
which
4?
is
What is the pressure
equal
of
to
number 4?
pressure of 1.
Yeah, P1, right? So table A3 again. And that's it. All right, this is how you can calculate the area of the enclosure very quickly. All right, so that's the TS diagram. Right? The advantage of this diagram is the enclosure is a perfect rectangle. And with a perfect rectangle, we can do a lot of things. All right, any questions regarding this TS diagrams? Okay, I think that's everything we will cover. All the topics will be covered in the midterm 2. Okay, midterm 2, we have 2 problems. We have 2 problems. Okay, the first one is very, very closely related to lecture 9.4. Lecture 9.4 is an example. 9.4 is one example. Make sure you watch that example step by step and make sure you understand every single step. Don't just memorize it because it won't help. You have to understand every single step, cover it, do it by yourself again to prepare. Okay. Also, you can study homework 4, problem number 3. Those 2 are very, very similar. The only difference between them is lecture 9.4, the example is the power plant, where everything is a control volume. You have to use the long version of first law. In homework, problem number 3, the example was an engine. Therefore, every step was treated as a closed system. Then you have to use the short version of first law. So by studying both of them, you can have a even better understanding of the whole thing, right? Okay, so when you solve a question like this in the exam, make sure you first identify if it is a closed system or a control volume. All right. Okay, so make sure you study that, those 2. Okay, and let's do a quick. So for example, if it is a power plant, right, this is going to be the diagram, P versus new diagram. It will be very similar to the example we did in class, lecture 9.4, but something will change. It won't be exactly the same, right? So for example, I will tell you, okay, for the one is the boiler. Now, at the inlet of the boiler, I have a mixture. What's going to happen to this diagram?
There wouldn't be a vapor dome because they're all mixtures.
You can still leave the vapor dome. All right, just 4 to 1 is the boiler, 4 is the inlet, 1 is the outlet. So now I tell you at the inlet of the boiler, water is a mixture.
4 is no longer going to be point F. It's going to be within the vapor dome.
Very good. You just move point 4 to the right. Move it under the vapor dome. And that's it. Okay. And then I say at the exit of the boiler, it's also a mixture.
So we move 1 to the left within the vapor dome as well.
Yes, that's it. You just move point 1 to the left under the vapor dome, and everything will still have the same shape. 1 to 2 will still be curved. 3 to 4 will still be curved. Okay. All right. And then what's your plan for H1 and H4? H1 and H4. Right now, what's your plan? Just look at the diagram we have right now. What's your plan for H1 and H4?
Go to the tables.
Yeah, H1 is equal to H, G. H4 is equal to
HF.
HF. Very good. However, if both 0.4 and 0.1 are mixtures, what's your plan to look for H1 and H4?
We find the qualities.
Very good. You will have to find quality first. Okay. All right. Very good. All right. So if quality is directly given to you, that's pretty good. But however, what if quality is not directly given to you? For example, I tell you number 1 is a mixture. And I tell you nu 1 is equal to 0.0001. Is there any way you can find x1 from here?
Yeah, you find new F, new G, you solve for quality, and then you
Yes,
find
very
HF,
good.
HG, and then solve for H.
Yeah, very good. Right, nu 1 can be equal to what? 1 minus x1 times nu 1f plus x1 times nu 1g. Nu 1f, nu 1g can be easily found from the table. So one equation with only one unknown. This is how you can quickly find x1. Okay. All right. I hope everyone has memorized the equation because it's going to save you some time for algebra. What is the equation? Actual minus f divided by
F minus G or G minus F.
g minus f. Yeah, very good. If you can memorize it, it's going to save you maybe 1 minute. Right? Okay. If you don't want to memorize it, that's fine. You can do the algebra by yourself. Okay. All right. It's going to be very, very similar to the lecture 9.4, and something will change slightly. Right. Be very careful. And the difficult part about this example was what? 0.2 and 0.3. That's the difficult part. So make sure you study the example, cover the solution, do it by yourself, so that you can, you understand how to approach every point. 1, 2, 3, 4. Okay, 4 to 1 is the easy one. 1 to 2, not difficult. 2 to 3, number 2, number 3 are the difficult parts. All right. Okay, so that's problem number 1, and you can study lecture 9.4 and homework problem number 3. Okay, so that's problem number 1. And problem number 2 are the 3 cycles. What are the 3 cycles we've learned in this class?
Carnot, power.
Not Carnot. Yes, power.
Refrigeration, heat pump, and power cycle.
Yeah, very good. Power cycle. What is it? What is the heat cycle? And what's the heat? Is usually the last one, right? Heat.
Yeah, it's refrigeration then.
Yeah, refrigeration cycle. Okay, so what you need to do is you need to be able to do the sketching for each one of them and do the analysis for each one of them. In our lectures, we have one example for each cycle. So make sure you study the analysis and also the example for each one of them. So for example, let's use, let's say power cycle as one example. So first of all, you need to be able to sketch, right? Square, inside a square, you have a circle. And how does a power cycle work? Power cycle gains heat from the high temperature, and what it does is to convert the heat into what? W cycle. And the second law tells us you have to lose heat to the low temperature. So you have to be able to sketch the power cycle. What about refrigeration cycle? How does a refrigeration cycle work? Refrigeration cycle, you can just think of the refrigerator, right? What it does is what?
You put work in. And
Yeah, it's very good. You have to pay for electricity, which is the work. Very good. Okay. And then what it does is, so think of the refrigerator, the inside of the refrigerator food decomposing, they release heat. So what the refrigerator does is to move heat from the cold inside to the warm outside. So what it does is to grab heat from the low temperature, which is the inside of the refrigerator, and then release the heat to the high temperature, which is the outside. And now if you take a look, what is the direction of heat transfer? The direction is from low temperature to high temperature. And this will never happen, right? Because in reality, in nature, heat transfer only happens from high temperature to low temperature. So if you want heat to transfer from low temperature to high temperature, what has to happen?
you have to put in work.
Yes, you have to pay. All right, what we pay is the electricity. That's why W cycle goes in. Okay. All right. What about heat cycle? What about heat cycle?
You also put in work, but you get exhaust out and you get heat in.
The heat cycle shares exactly the same diagram. So this is for power cycle, and this is for both refrigeration and heat cycle. The second diagram applies to both refrigeration and heat. Okay, but what's the difference? If you have a refrigeration cycle, what is the one we want? If you have a refrigeration cycle, keep something cool. What is the direct reason that you can keep the refrigerator cool? QC. QC, taking the heat away, is the direct reason why we can keep the refrigerator cool. So QC is what we want. However, if you're dealing with a heat cycle, what is the one we want?
QH.
QH is the one we want. Okay, same diagram, but we want different things out of the same diagram. Okay, and then we have something to measure the performance. For power cycle, what is the one we use to measure the performance?
Use not beta.
Efficiency, right? Efficiency, which is 1 minus TC over TH. For refrigeration cycle, what is the one we use to measure performance? It's not called efficiency, it's called what? Coefficient of performance, and it's beta. What about heat cycle? Heat cycle, we use gamma to measure the performance of the cycle. Okay, and how high can it be? Eta, beta, gamma. How high can they be? Right. The bigger those three numbers are, the better the performance is. But is there any upper limit?
0.62, I think.
I think
Eta
it's 1.
is not 1. Okay.
Oh.
There is an upper limit for each one of them.
Oh, it can't be bigger than its max.
Yes, it cannot be bigger than its max, and this max is determined by what? Second law of thermodynamics. So this is eta max. Okay, so how do you calculate each beta max, gamma max, and eta max? You have to be able to find from your notes. Okay, and let's say, okay, one practice we did was, okay, I have a new design of a refrigerator, and then what I ask you is to calculate beta max, calculate beta, and then do a comparison. If your comparison says your actual beta is even bigger than beta max, what does that say about your design?
Impossible.
It's
Yes, very good. That tells you your design is wrong. What is wrong? It violates
wrong. Second law?
second law. Very good. Just by checking those numbers, you can double check if your design violates second law or not. Okay. Same thing. If your gamma is greater than gamma max, then that means your design is wrong, violates second law. And same thing. If your efficiency for power cycle is even bigger than eta max, that means your design is wrong. It's not possible. Okay. And then one thing I noticed is you have to understand what is given to you. What I noticed before is, okay, I tell you students, oh, to warm up the house, this amount of heat is required. What is this heat given to you? Right, I say 4,000 megajoules of heat is required to warm up the house. Which one is this 40 megajoules? You have to
W
match.
cycle?
W cycle is what? W cycle is electricity. W cycle is electricity. And I tell you, to warm up the house, you need 40 megajoules of heat. Which one is that? It is QH. QH is given to you. All right. And then I say, okay, in the wintertime, my room temperature is let's say 70 Fahrenheit, and outside temperature is 20 Fahrenheit. Which one is which?
So the outside is TC. And
Okay, yes, outside temperature is TC, and
yeah,
70 is the
TH.
TH. Very good. So one thing I noticed is the calculation is not difficult. What I see most of the time is matching them wrong. So 40 megajoules is the heat used to warm up the heat. You need to understand this is what QH given to you. And then if you get this wrong, the calculation will be wrong. Okay, so make sure when you do the review, make sure you read the question clearly and then cover my solution so you can match what is given to you with what you need. Okay, if you mismatch them, then the calculation will be completely off, right? Everything will be wrong. Okay, so
whenever you say that it something needs like a certain amount of like joules, that's going to be the QH.
not necessarily. So for example, I can tell you, okay, I need 10 megajoules of electricity to power up the refrigerator. What is that?
Would that be the QC then?
No.
Or no, W cycle.
Yeah, W cycle. That's W cycle given to you. W cycle is the electricity you pay for. Right? W cycle is work, which is in the format of electricity, where QC and QH are heat. Heat. Okay. All right. So make sure you have to read the question clearly and match the information given to you with what is really it is, right? QC or QH or W cycle. You have to make sure which one is given to you. Okay. All right. All right. Okay, and maybe say, okay, let's say heat pump, steady state. It requires a power input of 1 kilowatts. What is this 1 kilowatts?
That's the work, isn't it?
Yes, which is W cycle, right? Power output. Power is just what? Power is work divided by time. Work is your electricity. So telling you the heat pump requires a power input of 1 kilowatts is what? 1 is equal to this W cycle. Okay. All right. Okay, I think that's it. That's the 2 problems. Okay. We've narrowed it down. Number 1, lecture 9.4, homework for problem number 3. Number 2, the 3 cycles. Okay. Any questions?
Professor,
Mm.
just to clarify for the second problem, are we gonna do all 3 or are you gonna just pick one?
Pick 1 out of the 3.
Okay, got it.
What if we do both? Extra credit?
There's only one. There's only one cycle. Okay,
Dang it.
Maybe wait for the final. But you guys are doing really, really well, right? You guys are doing very, very well, so you don't have to worry about anything. The midterm one has a really high grade, so most of you studied very well. But I do want to remind you again, do not waste your time to go to check.com or any other similar sites because I did the double checking. There's no question exactly the same on check.com. So if you do that, it's only wasting your own test time. So don't do that. Okay. Another thing is if you go to check.com and you find a similar question, you might think, oh, okay, I just need to change the numbers. I just need to follow their steps and change the numbers. I will be able to do it. That's not the case for this class. Why is that? If you see a question on check.com very similar to my question, it does not mean you just need to change the numbers. That's not the case. Why? Because in this class, if you change pressure or temperature, what's going to change? The phase will change. If I change the temperature higher, then it may become what? Superheated. And if I change temperature lower, it may become mixture. And after that, the approach will be completely different. Okay, so it's not just a difference in terms of numbers anymore. Just by changing numbers, the approach to solving this question will be completely different. So in short, there's no need to go to check.com or any other websites to look for anything similar. It's going to be a waste of your test time. You might as well just look at your notes and study a little bit before the exam. That's going to be the best way to prepare for it. Okay. All right. And again, please do not upload my exam to check.com because if that's found, we will have to contact the office on campus. We have an office on campus just to deal with that. And then they will contact check. They will delete information and give us your IP address, the person who ever submitted the material to check.com. We will have their IP address as well. It's just, it's not worth it, right? Not worth it. Just do the study. You will do well. From what I've seen in midterm 1, you guys are doing perfect. So you don't have anything to worry about. All right. And again, I've narrowed down the topics, so it won't take long for you to study at all. All right. Okay. I think that's my part for today's lecture. And any more questions?
Are the free cycles from chapter 6?
Yeah, in your homework, you did something like that, right? Was it chapter 6 or chapter 5? I think chapter 6.
Question 2 is very similar to what he asked us on the last homework we did. Also, he does examples of them in week 6. I mean, not week 6, on lecture 6.
Lectures. Let me take a look. I think it's week 6. Let me double check. There's 3 cycles.
Lecture 8.2 is power cycle. Lecture 8.3 is refrigeration. Lecture 8.4 is heat pump.
Yes, yes. Okay. So the 3 cycles, you need to refer to lecture 8.1 to 8